Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we shall go over the solutions for the problems in Self-Test 9 Form B. And beginning with today's discussion, you are encouraged to be using a calculator for doing all the work that's supposed to be happening. What that means is, as I'm doing the problems now, I will spend more time in setting them up and less time in doing the calculations. I will assume that either you have a calculator that you know how to use, or that you're doing these computations longhand. But since we've already practiced on the computations, I'm going to stress just the technique that gets us to the right formula. So without any further ado, let's go over to the board and start our solutions to Self-Test 9 Form B. And in all of these problems, unless otherwise specified, I've asked you to round off to the nearest hundredth. Okay? So the first problem says, at $172.93 each, how many coats can you buy for $11,000? There's a couple of ways of analyzing this problem before you begin. I mean, somehow you know you're going to be working with these two numbers. I sometimes, when I'm confused, which is quite frequently, I like to put in small numbers just to get a rough idea of what's happening. For example, I might put a 2 over here, and I might put an 8 over here. And I would say, at $2 each, how many coats can you buy for $8? It's not a very realistic problem, but using those numbers, I see I can buy 4 coats. How did I get it? 8 divided by 2. So now I just say what? 11,000 divided by 172.93. And you see, that's the advantage of the calculator. See, without a calculator, hopefully 8 divided by 2 doesn't bother me. But 11,000 divided by 172.93 might be a little bit more troublesome. And to handle that, here's something else you can do. Instead of putting in a silly number like 8 over here, why not put in a number like 12,000? And instead of putting in a number like 172.93, put in something like 200. Then the problem would say, at $200 each, how many coats can you buy for $12,000? And you see, now rounding off, 200 goes into 12,000, roughly 60 times, and you begin to sense that the answer is going to be around $60. So once you know that, you're in pretty good shape. And once you know that, how do we proceed with the problem? Well, you could argue something like this. You could say, since each coat costs me $172.93, whatever number of coats I buy, it's going to cost me $172.93 that many times. So the formula would be what? $172.93 times the number of coats equals the total cost in dollars. In this particular formula, in this problem, I'm told that the cost that I have to spend is $11,000. So the problem becomes $172.93 times blank equals $11,000. That's, again, a problem that looks like multiplication, but it's really division. And so what it really boils down to is what? What number, I left that little equal sign here. That's okay. See, if in this case, blank is what? Blank is $11,000 divided by $172.93. Okay? And so we just do this division, and that should give us the answer. All right? And again, if you didn't want to do the problem that way, how would we use our dimensional analysis that we talked about in this unit? You say $11,000 equals blank coats. And you say, okay, I want to get rid of the dollars and bring in the coats. So since dollars occur in the numerator, I'll put them into the denominator. Then I'll put coats in the numerator. And what's the relationship? $172.93 equals 1 coat. Now you see what happens? My numerator, first of all, my dimensions tell me that the label is coats, which is what I want. My numerator is 11,000. My denominator is 172.93. Therefore, because it's in the denominator, I know that the answer to this problem is 11,000 divided by 172.93. That's where I go to work either with my calculator or longhand. With my calculator, I enter 11,000. I press the division sign because this is in the denominator. I enter 172.93, press the equal sign. Lo and behold, an answer lights up. On my calculator, it was 63.609553. And what does that mean? That's how many coats you can buy. Well, you can't buy a fractional number of coats. So really what it says is what? You can buy 63 coats and a certain fractional amount left over. Now, if you wanted to find out how much change you had, simply take the number of coats that you could buy, multiply that by $172.93, which you can also do on the calculator. That would come out to be $10,894.59. See, I'm not going through the calculations now because I assume you can do those on the calculator. And now, since I started with $11,000, I simply subtract this from $11,000, and that tells me how much money I have left over. In other words, what this problem really says is, with the $11,000, I can buy 63 coats and have $105.41 left over. And if you want to see another way of getting that, remember, each coat is worth in dollars $172.93. So if you took $172.93 and multiplied that by 0.609553, hopefully you should get what? The same $105.41 that you got this way. See, again, this is not money, it's the fractional part of a coat. And in this problem, when you're dealing with money, each coat is the same as what? $172.93. And all the problems are done pretty much the same way. Here's another one on unit pricing. It says a tube of toothpaste costs $2.39 for 2.9 ounces. What is the price per ounce? If I do it in dollars per ounce, that means what? Dollars, which is 2.39, divided by ounces, which is 2.9. You see, now, once I have this, the advantage of the calculator is that I just enter the 2.39, press the division sign, enter 2.9, I hit the equal sign, and I get a whole maze of numbers here. And this is what? 0.824137931, and that's what? Dollars per ounce. If I round this off to the nearest hundredth, that's going to be 82 cents per ounce. On the other hand, if I want the answer in cents, it's 82.4137931 cents per ounce. And so if I round this off, it's 82.41 cents per ounce. The way I worded the problem, I was looking for 82 cents an ounce. If you gave me this answer, that's okay too. Because you know what's interesting? I fell victim to my own admonition, or to lack thereof. You know what I did? I always told you to put in labels. Put in labels. And what did I wind up doing? I said round off to the nearest hundredth, but I didn't say nearest hundredth of a dollar or nearest hundredth of a cent. Therefore, I have to accept either answer over here. Well, that's the way it goes. At least get one of these two answers, all right? Third problem says that students sell tickets for charity to raise money as a fundraiser. They sell the tickets for $2.89 each. Their commission is 55 cents. And the question is, based on the price of the ticket, what percent is this? And this is an interesting question. You see, the point is, if I tell you that I made 55 cents on a ticket, that doesn't tell you whether that was a good income or a bad income. See, if the ticket sold for 55 cents, then I've kept everything. That's a pretty good take. On the other hand, if the ticket was $55, 55 cents isn't much at all. So basically, what we like to do is to convert things to a percent based on what we made compared to what we had to pay, or what we had to bring in. So in this problem, what we're saying is what? For every $2.89 ticket you sell, you make 55 cents. In other words, you're making 55 cents per $2.89. The problem is, to use a rate, we agreed that you have to compare like things. It's cents compared with cents, dollars compared with dollars. So we have to reword this in the form that says you're making 55 cents for every 289 cents you're selling. So what fractional part are you keeping? 55 out of the 289. And the question says, as a percent, what is that? And the answer is it's 55 289ths of 100%. Remember how we read this? This says what? At a rate of 55 out of every 289, how many do you take out of 100? The only difference between this chapter and the earlier chapters is that now I'm not going to do any of the work. I'm going to let my calculator do that. You see, I multiply the numerators, so the 55 has to multiply the 100. That I'm a big sport about. I do that in my head, 5,500. The denominator is a 289 times 1. So the percent is what? 5,500 over 289. That's 5,500 divided by 289. I take my calculator, I enter 5,500, I press the division sign, I enter 289, hit the equal sign, I get 19.03114, etc. And rounding that off to the nearest hundredth, I see I get 19.03%. Roughly speaking, I'm getting 19% of whatever the sale price is of the ticket. It's up to me to decide whether that's a good return or a bad return, but that's the percent I'm making on each ticket. Now we come to something fairly realistic, and that's, well, I hope it's realistic. It's called getting a raise. And very often in today's economy, people don't do things the simple way. They don't say we'll give you a 7% raise or an 8% raise. They'll say we'll give you a 7 2/3% raise. It sounds like they worked harder on the contract. Banks do the same thing. Instead of paying a low 5%, we'll now pay you a high 5 1/4%. But the point is that the theory still stays the same, and I just thought I would throw in those kind of numbers just to have you see how it works. And problem number 4 says you get a 7 2/3% raise. What is your new salary if your old salary was $1,537? I've abbreviated the problem. I think this was monthly salary. I don't want anybody to think that we're paying our people badly here. It's not daily, but it's also not yearly over here. Well, you see, again, if numbers like 7 2/3 bother you, work with 7% and 8%. See, 7 2/3% is between 7 and 8%. You see, if you get a 7% raise, that means that for every dollar you were making before, you're making $1.07 now. So in other words, if you were making $1,537, you're now making what? $1.07 1,537 times. So in other words, at a 7% raise, you would be earning $1,644.59. What would an 8% raise mean? It means for every dollar you were making, you're now making $1.08. So for $1,537, you're making $1.08 1,537 times. If you multiply those numbers, and you don't have to use the calculator, but it's easier, or at least quicker, that comes out to be $1,659.96. And since we're dealing with 7 2/3%, which is between 7% and 8%, it tells us that whatever the right answer to this question is, it's going to come out to be between these two extremes. And knowing that, we can now figure out what's going on. And how do we do that? Let me show you a nice way of handling this. See, it's kind of messy to work with this 2/3. It's very messy, in fact, to work with this 2/3. So what we're going to do instead is to use that little trick that I taught you during a previous module lecture. If the decimal point weren't here, this would be 107 2/3. But what would the label be? 107 2/3. Remember, we only count the digits, not the fractions. That would be 107 2/3 hundredths. As a mixed number, 107 2/3 becomes what? It's 3 times 107, which is 321, plus 2 is 323, over 3, but hundredths means divided by 100, and to divide a fraction by 3, we tack on 2 more zeros to the denominator. In other words, 107 2/3 is the same as 323 over 300. And if you want to check this, 1.07 is 107 hundredths. That's the same as 321 over 300, you see, multiplying numerator and denominator by 3. And 1.08 is 108 over 100. And if we multiply numerator and denominator by 3 here, we get 324 over 300. And notice that 323 is 2/3 of the way between 321 and 324. So it checks out. But you may not be used to seeing the problem done this way. In other words, what this says is that if your raise is 7 2/3%, for every $300 you were making with the old salary, you're now making $323. That's all that says. So now, armed with that information, we can go to the formula. Namely, instead of multiplying the old salary by 1.07 or 1.08 to get the new salary, see, I'm starting to teach you formulas already. I start to use abbreviations like old salary, new salary. You see, what I have now is what? 323 over 300 times the old salary equals the new salary. In other words, basically what you're going to do is divide the old salary by 300, and for every block of $300 you were making with the old salary, the new salary is going to pay you $323. Now, how do you handle this problem? In this problem, you're given that the old salary is $1,537, so you simply multiply that by 323 over 300. And how do you do that on the calculator? You multiply the numerators and divide by the denominator. Remember, whenever there's no denominator, you can always assume that it's 1. So on the calculator, you take 323, times that by 1,537, get the answer, divide that by 300. And by the way, you can do these in any order you want. You could have started with the 323, then divided by the 300, then multiplied by the 1,537. But once you do that, the calculator will show you something like 1,654.836667. We round that off to the nearest penny in this case, the nearest hundredth, and that says that after the raise, you were making $1,654.84, which, by the way, checks with the range that we said the answer had to be in. Can we take a look at that? In other words, we said before we started the problem that the answer had to be between $1,644.59 and $1,659.96, and notice that at least the answer that we got is in that range, and that shows us that basically we're doing things okay. Part B is the same type of problem, but now it involves a little bit more reading comprehension. In Part B, the only difference is that we're now given the new salary. We're given the salary after the raise, not the salary before the raise. You see, the formula is still 323 over 300 times the old salary equals the new salary. The difference is the $1,356.60 replaces the new salary. So in terms of a division problem, this problem says what? The old salary is equal to $1,356.60 divided by 323 over 300. And to divide by 323 over 300, you multiply by 300 over 323. You see, without the calculator, we would still have a lot of work to do now. With the calculator, once we're down to here, the problem is just about over. Just multiply this by this, then divide by this, and in this case, the answer comes out to be $1,260 exactly. And there is a helpful hint, hopefully a helpful hint, when you're doing things and you're not sure which answer goes with which. Just try to remember that hopefully you make more after the raise than before. And I hope my boss is listening. Yeah. That's the best way to do it. If you find out after you raise, when you compute it, that you're making less after the raise than before, you know you've used the formula incorrectly, all right? Now, here's a case where we apply the material that we've learned to something that's very typical in a statistics type of situation, a quality control type of situation, where we want to measure what the success rate is. For example, on the assembly line, we want to know how likely is it that if we pick a part at random, that it's going to be a non-defective part. See, that's a very, very big thing in operating costs. If you don't have many replacement costs, you can sell at a lower rate. Quality control, that's the phrase that we use, is an in thing right now and will probably continue to be for a long time. Well, here's a non-controversial example of that. 729 soldiers take an eye test. I've used a few abbreviations over here just to get more board space to write. 123 of the 729 fail the test. And the question is, at that rate, what percent pass the test? And again, notice how reading comprehension comes in. The 123 modifies the number that failed. The percent modifies the number that passed. You see, the failure rate was 123 out of the 729. Since either a person failed or they passed, if 123 failed, the difference between 729 and 123 must be the number that passed. So the failure rate is 123 out of 729. The passing rate is 606 out of 729. Now you have to read the problem to see which they want done over here. They want the passing rate. So what you want to know is, at a rate of 606 out of 729, how much is that out of each 100? See, out of 100%. The most common mistake that people make here, assuming that they get this far, is they take 123 7/29ths of 100%, which on the calculator is very easy to do. 123 times 100 divided by 729. That comes out to be 16.872427, etc. And if we round it off to the nearest hundredth, that's 16.87. But what is that? This is the ratio of the people who failed. You see, 16.87% is the failure rate, the failure percentage, not the passing percentage. Since we want the percent that passed, the total number of people, the 100%, either passed or failed. Whoever didn't fail must have passed. So now we have to remember to subtract the 16.87% from the 100%. That gives us 83.13% as the passing rate. If you wanted to do this problem in one step, notice that the passing rate as a fraction is 606 out of 729. So if you take 606 out of every 729, how many are you taking out of 100? It's 606 729ths of 100. And so you do what? You multiply the 606 by the 100 to get 60,600. Your denominator is 729. Now on the calculator, you enter 60,600, press the division sign, enter 729, hit the equal sign, you get 83.127, etc. And notice that if you round that off, it's 83.13, which is the same answer we got this way. In fact, if you take this number and add that on to this number, even without rounding off, you see that should add up to 100%. But again, what I'm trying to have you see is the reading comprehension. You not only have to know how to take percents, but percent of what? What do you subtract from? What do you add on to? This is all part of the problem. And nobody tells you that. You have to figure it out. Problem number 6 is an investment type of problem. You bought a house for $24,876. 4 years later, you sold it for $37,080. Well, now you know, if I subtract these two numbers, I know how much money I made on the sale. But I've had the house for a certain number of years. If I had left the money in the bank, money would have been accruing over each year. So a very natural question that I could ask is, what was the average annual increase? See, what was the average increase per year? Increase per year first means find the increase. In other words, the house increased from $24,876 to $37,000. I subtract. That tells me that the increase was $12,204. That happened over 4 years. So this number of dollars divided by 4 years, see, I should put that in to remind you, will give me a label of dollars per year. So if I do this division, and again, I did this out the long way, it's not that long, to show you shouldn't become a slave to the calculator. You could take 12,204 and divide by 4, but if the calculator isn't handy, it's much quicker to do this, hopefully, than to go looking for the calculator. At any rate, that would say that on the average, each year, your house increased in value by $3,051. But now the question is $3,051 a good return or a bad return? And the answer again says it depends on how much money you invested for the house. What were you making that $3,051 on? It was on an investment of $24,876. So based on the price you paid, the question says what was the average percent increase? You made $3,051 per $24,876. So I take that fractional part of 1,000, and that's going to give me the answer to the problem. In other words, I take 3,051 multiplied by 100, that gives me my numerator. Then I divide by 24,876, because that's my denominator, and that will give me 12.2648, etc. percent. And that rounds off to the nearest hundredth to be 12.26%. And I'd like to show you again how people can be tricky. It's a very small point, but I just want you to notice this. See, percent is important because it tells you a rate. You see, it tells you more. It's like when we said before, if you say you went 60 miles, that doesn't say anything about how fast you were going. Did it take you 1 hour? Did it take you 2 hours? But if you say you were going 60 miles per hour, then you know how fast you were going. You see, let me give you an example. Suppose you buy something at $4 and you sell it at $5. You therefore made $1. $1 based on what? Well, if you take the price you bought it at, you made $1 out of 4, which is a 25% return. If you based it on the price that you paid for it, that you sold it for, you're making $1 out of 5, which is a 20% return. In other words, suppose a bookstore sells a book at $5, and they say, well, we're only keeping 20%. Remember, they didn't pay the $5. All they paid was the $4. So by keeping $1, they're making $1 out of their $4 investment. In other words, they're getting a 25% return on what they paid. The 20% return is only on what came in. You see? But anyway, that's not that crucial. I just wanted to make sure you understand that. And now here's another problem, almost like the eye test with the soldiers, but stated a little bit more in terms of what we find in quality control. A test is accurate 91.4% of the time. In other words, statistically, over a long period of time, we've found out that this test, by the way, what does it say in terms of whole numbers? 91.4. 91.4% means 91.4 per 100. If you move the decimal point one place to the right, in both of these, you get 914 per 1,000. And what that says, roughly speaking, is that when you did this test, out of every 1,000 times you tried it, it turned out to work on the average 914 times. And now what the problem says, to the nearest whole number, based on this success rate, how many times can you expect the test to be, and listen to the wording, inaccurate if it's used 540 times? Well, you see, the 91.4% refers to the accuracy rate. The inaccuracy rate must be the difference between the 91.4% and the rest of the time. See, 100% minus 91.4% is 8.6%. That's the failure rate, because either it fails or it works. It's either accurate or inaccurate. If it's accurate 91.4% of the time, it must be inaccurate the rest. That's 8.6%. So in other words, it's going to fail what? 8.6% of the times that you try it. And since you're trying it 540 times, the failure rate would have been what? 8.6% of 540. Move the decimal point 2 places to the left to remove the percent sign, because you're dividing by 100. That's 0.086 times 540. You can either do that longhand or on the calculator. It comes out to be 46.44. Rounding off that to the nearest whole number, you get 46. And what that says is, if you try this thing 540 times, you should expect it to fail 46. And that's another thing that statistics is interested in. What if it failed 47 times or 48 times? Is that still a reasonable answer? Are you supposed to expect something like that to happen? You say, okay, nothing's perfect. But what if it failed 147 times? Is that close enough to the 46 to become suspicious or not? See, that's what statistics also is all about. When there is a deviation, how large an error can you allow and pass it off as being insignificant, and when do you have to say that the theory has been violated? And that's just roughly some of the ideas that go on here. Now again, the most common mistake that people make is they see the 91.4%, they see the 540, they say, what the heck, I'll take 91.4% of 540, which you can do. Namely, percent means divided by 100. That means move the decimal point 2 places to the right. That gives you 0.914. Of means times. You multiply that by 540. On the calculator again, 0.914 times 540 equals 493.56. You round that off to the nearest whole number. The answer is 494. But what is that 494? Right now, it's just an adjective. Adjectives have to modify nouns. Was this 494 failures, accuracies, or inaccuracies? Well, the 91.4% is an accuracy rate. So this is the number of times it's accurate. And so if you try it 540 times and it's accurate 494 times, then I've got to subtract the 494 from the 540 to see how many times it was inaccurate. And fortunately, as always happens in math, if you don't make a mistake, no matter how you do the problem, you're going to get the same answer. It's inaccurate 46 times out of 504 tries. Okay, let's look at another problem. At 39% off the list price, an item sells for $85. Okay? How much are you saving on the list price? This is very similar to a problem we did during the lecture. But during the lecture, we didn't say how much money are you saving. We said how much was the list price. See, again, listen carefully. This doesn't say if it sells for 85% at the sale, what was the regular price? It says how much do you save by buying it at this price. You see, you not only have to do a lot of work, you have to do a lot of thinking. And here's the rub. When you had lots of computations to do, I didn't want to give you too much thinking to do, because it would give you too much to concentrate on at the same time. But if the calculator is going to do all the dirty work for you, now you have time freed up to think. You see, in these problems now, if you're using the calculator, it should only take you a few seconds to do all the computations that you need in these problems. What's going to take the time is setting the problem up. Okay, so let's see how this thing here works. The 39% is off, and the question says, after the 39% is taken off, you're still paying $85, and the question is, how much are you saving on this sale? Let's go back to the baby way of doing this. If the list price were $1, since it's 39% off, you're saving 39 cents. And if you're saving 39 cents, the sale price must still be what? 61 cents. You see, this number plus this number still is going to add up to the list price. See, if it was $2, you're saving 39 cents twice, that's 78 cents. And the sale price is 61 cents twice, which is $1.22. And to make a long story somewhat shorter, you see, as the list price goes up by multiples of 1, the amount you save is going up by multiples of 39 cents, and the sale price is going up by multiples of 61 cents. So, in other words, when you're on the 50th row of this list, if you're in the 50th row of this chart, the entry in the list price is going to be 50. The entry in this column, the save column, is going to be 50 times 0.39, and the entry in this column is going to be 50 times 0.61. You see the multiples of 1, the multiples of 39 cents, the multiples of 61 cents. In other words, the list price multiplied by 0.61 is going to be the sale price. And what that says in plain English is that the 39% of the list price was the savings. Whatever you don't save, you're still paying. So if 39% of the list is the savings, 61% of the list is the sale price. Okay? But they didn't tell me the savings, they told me the sale price. You see, how do I know which formula to use here? Well, I don't know the list price, so I'm in trouble. I can't base it on this. If they told me how much I saved, but didn't tell me the sale price, I would have used this formula. Since they told me the sale price, but not the savings, I'm going to use this formula. And by the way, whichever one I use, I get the other one as a freebie. In other words, if I know this number, I subtract it from the list, that gives me the sale price. If I know the sale price, I subtract it from the list, that gives me my savings. If I know the savings and the sale price, I add them together, and that gives me the list. Isn't that neat? Well, let's go on then. So in this particular problem, I'm told that the sale price was $85. Therefore, 61% of the list price has to equal $85. So the list price times 0.61 equals $85. That's a division problem, namely, it looks like multiplication, but when I solve for the blank, I get what? See, blank times 0.61 equals 85, says blank equals 85 divided by 0.61. That might take a little while longhand, but with the calculator, that's very easy. I simply take the 85, I divide that by 0.61, rounding it off to the nearest cent, I write down what I see on my calculator. That's $139.34. That was the list price. That would be great, except that's not the problem. The problem didn't ask me what the list price was. The problem said, how much did you save? Well, if the list price was $139.34 and I paid $85, the difference must be what I saved. So I simply subtract this, which, by the way, is a very easy subtraction problem even without the calculator, and I find out that what I saved was $54.34. And notice this, without the calculator, if I know what I'm doing, I can solve this problem very easily. With the calculator, if I don't know, I'm supposed to find the $139.34 and subtract the $85, I'm in trouble because I don't know what to do. But anyway, that's the way this works. I've drawn a very rough chart here so that you can see what's going on. You see, if I look at this rectangle as being the list price, you see, the rectangle represents the whole 100%. The 39% off is what I'm saving. The 61% on is what I'm still paying. So what's happening is the 85 is what I'm paying, so the 85 goes in this column, and so what this says is 61% of the list price is $85. That's a pictorial way to see this if you prefer. At any rate, let's get on with the last part of the assignment because there's some very interesting things to be discussed in that part of the assignment. Problem 9 and 10 form a very interesting pair. Well, let me change that a little bit. They're kind of boring. That's quite a change from interesting to boring. They're boring in the environment in which I've given them, but they have tremendous application to something very important. And let's just do the boring part first and then see what happens later. See, we're told that the cost of groceries are increasing 7.3% each year. And the question says, at this rate, if the grocery orders cost $200 now, how much will the same order cost 2 years from now? Now, here's the trick to this problem. I'm going to do it gradually for you. See, 7.3% says that you're increasing by 7.3 per 100. And to put whole numbers in here, multiply both numbers in the ratio by 10. So what this says is the cost of the groceries is going up $73 for each 1,000. What does that mean? For each 1,000 the groceries cost, this year, next year they're going to cost what? The 1,000 plus the 73. And so what that says is you're going to have to pay $173 for each $1,000 that you're paying now. And by the way, how do you write 1,073 over 1,000 as a decimal? Without the decimal point, you see 1073, okay? You're dividing by 1,000. To divide by 1,000, you move the decimal point 3 places to the left. So there's your 1.073, which, by the way, checks with the fact that if the cost of groceries had gone up by only 7%, every dollar this year would cost $1.07 next year. And if it's gone up by 8%, every dollar this year would have cost $1.08 next year. And notice that 1.073 is right where it should be over here. In fact, you could have done this in one step if you felt confident. Most people don't like to deal with tenths of a cent, but it doesn't matter. Whichever way you get this, what you're saying is, look, in the first year, this is the tricky part. See, in the first year, the order was $200. For every dollar, I had to pay $1.073, so I'm paying $1.073 200 times. And when I multiply that out, I get $214.60. Here's the tricky part. The second year, this is now the price. See, it's not $200 anymore. That was gone. See, it's the same thing when they talk about the cost of living index. They say, oh, this was great. The cost of living index was only 0.3% this month. You say that's terrific. It's not so terrific. It's 0.3% more than what it was before. In other words, if this stuff had been going up dramatically, you're still increasing over that. All it says is we're still going up, but not as much. You see the idea that I'm driving at this way? You see, what happens is the $200 is no longer the price after the first year. After the first year, the price is $214.60. That means that the increase the second year is applied to the $214.60. You don't multiply this number. You see, you don't just double the increase here. You have to multiply this whole thing by 1.073. You see, it's 1.073 times 1.073 times 200. And that answer comes out to be $230.27. You see, to put this in the form of something that you can see more readily, you start with the old price. 1 year later, this is the new price. But the new price for the end of the first year is the old price at the end of the second year. So now that price is what gets multiplied by 1.073. So you're multiplying by 1.073 twice. That's called the square, remember? 1.073 times 1.073 of the old price gives you the new price. By the way, on my calculator, I can multiply 1.073 by 1.073, and that gives me 1.151329. Look how neat I throw these numbers around, because I'm just reading them off the calculator. So it says this number multiplied by the old price gives me the new price, no matter what the old price was. In particular, if the old price is $200, I multiply that by this, and that gives me the $230.27. Okay? And by the way, what if I wanted to see what's going to happen the third year? Now I start with this number, and that's what gets multiplied by 1.073. And each year, I'm going to keep doing that. And I'll show you an application of that in just a few minutes. But let's finish off problem number 10, which is the mate to this problem. See, under the same conditions as in the previous problem, well, what were the conditions in the previous column? the cost of the groceries is going up 7.3% every year. So now the problem is worded in reverse. It says if 2 years from now the groceries will cost $200, how much will they cost now? In other words, in terms of the future, looking ahead to the future, if something is going to cost you $200 2 years down the road, what can you get it for right now? See, maybe it's better to buy it now than to wait until the future. See, that's basically how estate planning goes, as I'll mention in a few minutes. But let's just solve this problem first. You see, no matter which way we do it, whether it's problem number 9 or problem number 10, this is the formula. 1.151329 times the old price equals the new price. Old price, new price. The only difference in this problem is that now the $200 represents the new price. The $200 represents the new price. So now I replace the new price by $200. The problem becomes what? 1.151329 times the old price equals 200. So the old price is 200 divided by 1.151329. And you start to sense what a messy problem, not hard, but cumbersome problem this would be without the calculator? See all those digits? But with the calculator, you punch these numbers in, round the answer off to the nearest cent, and out comes $173.71. In other words, if the groceries are going to cost me $200 2 years from now, right now I can buy that same order for $173.71. And this is what I mean by what I call estate planning. There are two ways to look at this. One way is, suppose I want my youngster to go to college, and I don't have the money right now to send my youngster to college. What can I do? I can start putting away an amount of money now far enough in advance so that by the time he goes, the money will be there. And that's exactly, in a sense, how tax-sheltered annuities work. Let's suppose you were putting your money into the bank, roughly speaking, at 12% interest. So roughly speaking, that means that every 6 years, your money that's been put away will double. Now watch what that means. Suppose you put away $1. At the end of 6 years, you've got $2. Now, whatever you have is doubling every 6 years. At the end of the 6th year, you've got $2. So during the next 6 years, it's the whole $2 that doubles. So after 4 years, you now have $12. You have $4 after 12 years. During the next 6 years, it's the whole $4 that's doubling. So after 18 years, you have $8. Now, since the amount that you have, you see what's happening over here? This $8 is the new amount at the beginning of this time period. During the next 6 years, that $8 doubles and becomes $16. And during the next 6 years, that doubles and becomes $32. And then during the next 6 years, this doubles again. This is called exponential growth, and we deal more with that in later modules. But 36 years later, the $1 has grown to $64. At which point you say, well, I ain't going to get rich that way. Well, that's only per dollar, per 1 unit. What if I had put in $10,000? See, 10,000 would have become, this is even more, anyway, in other words, I even wrote this thing down incorrectly over here. I don't know what made me write this. You see, what's saying is, whatever amount of money you put away, it's worth 64 times that amount 36 years later. What's 64 times 10,000? 64 times 10,000. I get a little bit tired here and get carried away, so I lost some of the effectiveness of the answer. If you put money, if for some reason you could get a hold of $10,000 and you put it away at a relatively modest 12% annual interest compounded annual, in other words, every year the interest adds on to the previous interest, after 36 years, you're going to have $640,000 without doing anything. And that's how these tax-sheltered annuities work. You're putting away $10,000, and without you doing anything, it's worth $640,000. And the interesting point is people say, yeah, but I got to wait 36 years for that. Well, if you're only 25 when you do this, you're going to be just about at retirement age. And the guy says, yeah, but I still got to wait 36 years. Great. If you're lucky enough, you're going to live 36 years regardless of whether you save it or don't. It's much nicer to have the $640,000 there. I mean, people say to me things like, yeah, but the cost of living is going to go up. all kinds of bad things are going to happen? My answer is simple. No matter how bad things are, my intuition tells me I can survive it better with $640,000 than without it. Okay? It's like the fellow who was complaining. He hit 1,000,000 to 1 shot. He bet $10 on something, and he hit 1,000,000 to 1 shot. And he says, how do you like that? With my luck, the one time in my life I hit 1,000,000 to 1 shot, all I bet on it was $10. I mean, $640,000 is a lot of nice money. The problem is that most of us don't have the $10,000 to invest all at once, and that's why we take a certain portion of our income and try to put that away. I've never lived by that philosophy, but people tell me that one of the first things you should do with your paycheck is pay yourself. Put something into the bank, let the stuff grow, and all of a sudden, when it comes time to retire, all this money that you didn't even know about is there ready and waiting. And isn't that an uplifting story to end this lecture with? I think it is anyway. So next week, our next lesson, we're going to go into some more applications. That's what the rest of this course will be. Practice with your calculator. Start to feel comfortable with reading problems that you're not familiar with. Go into a new situation with the feeling, until proven otherwise, you can do it. And until next time, study hard, have fun, stay young.